Hello, everyone, and welcome to Chemistry Workshop. In this episode, we will analyze the bioinspired synthesis of Spirochensilide A and B and abiferrin B as well by the Heretsch group in 2022. Spirochensilide A and B are a pair of epimers differing only in the configuration at C3. Spirochensilide A is isolated from a Spirochensilide having 6 rings with 2 asymmetric spirocarbons and a pair of transfused rings. It also has 2 pairs of vicinal quaternary stereocenters and some sterically hindered functional groups. It is also interesting in the pharmacological sense in that they are moderate nitric oxide inhibitors, which could be of diverse use in medicine. Nitric oxide, being a key biological messenger, participates in a lot of biological functionalities like dilating blood vessels, immune responses, and more. Radical reactions have been recently put to the test in synthetic fields, and there are a lot of work in total synthesis utilizing radical cyclizations starting from the 1980s. Radical cyclizations are useful in that they can readily access hindered stereocenters previously hard to access through polar attacks, and they can also be done in a rather neutral environment and can be compatible with a lot of other functional groups. Also, as demonstrated in the second example here, a tandem radical cyclization can be used to construct a multitude of hindered stereocenters and string rings at once, being a quick and efficient tool for a synthetic chemist. Also, further reduction of radicals post-cyclization can create anions, which is only used in limited groups and terminated process in example 1, but other cases where this anion further participated in aldol condensations and the like have been seen and used. This work by the Heretsch group employed a radical polar crossover by oxidizing the radical to a cation modeled after the biogenesis pathway. Is also a great example of the utility of radical chemistry. The group proposed a possible biogenesis pathway for Spirochensilide A. They expected that the pathway will start at abiferrin L and an alkoxy radical generation. Then, a 1,5 hydrogen atom transfer results in a carbon radical, which then oxidizes and undergoes 2 Wagner-Merwin rearrangements to form abiferrin B. Then, abiferrin B undergoes epoxidation and an amine wall rearrangement with oxidation and spirolactinization furnishes Spirochensilide A. Thus, following the biogenesis pathway, the group formulated the total synthesis pathway starting from lanosterol. Lanosterol's hydroxyl group at C3 is first protected by an acetate, and then the double bond in the side chain is oxidatively cleaved through the Mu von Rudolph reagent to furnish carboxylic acid 4. This carboxylic acid is then subjected to photocatalytic decarboxylative olefination and then a hydroboration to afford alcohol 5. Then, through the generation of an alkoxy radical at C23, which then selectively forms a carbon radical at C17 through a 1,5 hydrogen atom transfer and an oxidation to result in a carbocation, Wagner-Merwin rearrangement, and then attacking by the hydroxyl at C23 forms 6. Then, titanium tetrachloride, a Lewis acid, initiates the second 1,2 shift and the ether cleavage to result in alcohol 7. This alcohol 7 can be converted to Spirochensilide A and B through more steps, but it can also form abiferrin B through oxidation of a side chain alcohol, addition to the formed carbonyl, further oxidation, and finally deprotection combined with base-induced rearrangement of the double bond between C25 and C27 to set C23 and C25. To get Spirochensilide A and B from 7, we need to form the spirocycles present in Spirochensilide A and B. The Heretsch group decided to construct the C8 through a mean water rearrangement from epoxide, but all traditional epoxidation methods have failed to produce the alpha 8,9 epoxide selectively, and all resulted in a beta 14,15 epoxide being formed. However, this beta 14,15 epoxide immediately opened and formed a hydroperoxide upon exposure to air, indicating its high reactivity. Thus, the group explored the possibility of exploiting this reactivity of the 14,15 double bond and formed a halohydrin through a vinylogous attack of water after forming an iodinium ion from N-iodosuccinimide. However, intramolecular SN2 attack on the formed hydroxyl group and elimination of the iodine was unfavored, and through heavy experimentation, the group found that a condition of aqueous silver nitrate and hexafluoroisopropanol with N-iodosuccinimide resulted in the desired spirocyclic ketone 8. Then, starting from ketone 8, oxidation by this margin per adenine, and then appendix oxidation formed carboxylic acid 9. Then 9 subjected to the white chain catalytic system, and lactone 10 is formed, which is then treated with a Grignard reagent to form a hemiacetal, and then treated with copper chloride and palladium chloride to get spirolactone 11A, which has the appropriate configuration at C3 for spirochensilide A, and the synthesis is completed by adding a methylene and isomerization at C25. For spirochensilide B, the configuration of C3 needs to be first inverted through oxidation by dimartin per adenine and reduction by L-selectride, and then through the same conditions with the exception that the isomerization of the double bond is carried out by rhodium, yields spirochensilide B, completing the synthesis. This amazing synthesis of spirochensilide A and B and ibuprofen B demonstrated the novel strategy of selectively forming a carbocation through a radical polar crossover, a novel strategy for the biomimetic mean wall rearrangement, and a novel oxidative spirolactone formation strategy for 1,6-dioxyspiral 4,5-decanes. I hope that this video has been interesting for you, and if you have any questions or suggestions on how this can be done better, feel free to put them in the comment section. The next episode will be about the synthesis of chuchuane by the Lee group. I hope you have a great day and see you next time. Bye.